A game has the n rooms and m tunnels between them. Each room has a certain number of coins. What is the maximum number of coins you can collect while moving through the tunnels when you can freely choose your starting and ending room? To travel between the tunnels. Each finally there are m lines describing the tunnels. Each has the integer a. There is a tunnel from room A to room B. Each tunnel is a one-way tunnel. Okay. Directed graph. We have a directed graph with n nodes, m edges, and every node has some coins, and we can start from any node and stop at any other node, and we have to find what is the maximum number of coin we can collect in this traversal. Okay, so is it, if I find, so what should to get the maximum, is it always positive? Okay, yeah, so I think as many nodes as I can, as many nodes I can cover, that would be good. So that means if in a strongly connected component I would want to visit all the nodes, and then in the second strongly connected component I would like to visit all the nodes, and the third one also. But after, let's see, so if we have, let's say, some, if I have some strongly connected component, this one, this one, this one, this one, this one, so these are CCs. So if I can visit, so it also comes from here. So what I would like to do is, I would like to visit all these nodes inside this, because from any node I can visit any other node. Okay, that is fine. Now after covering this, I would like to go to, I would like to find such a path such that this sum is maximized. Where will I stop? At the leaf node, at the sink nodes, right? Yeah, without degree 0. Is it the directed acyclic graph? I think from the original graph, if I convert it to the strongly connected component graph, which is a DAG, right? So in this DAG I will have some ordering, so it will have a topological ordering. Okay, let's say this is the new graph. It can again go here, it can go here, let's say it can also go here, it can also go here, it can go here. So if this is the topological sort in the end, or let's say we have one more and it goes here, what will happen now? So I can end up any of these nodes. I can end up at any of these sink nodes if I start from any of the starting node, because that would be the, I would like to, so if this is one path, or I can go from here using this path or this path, it doesn't matter, because I would get the coins at the node only. And then if these two, okay, I can also go from here and then come here. Is it a DP? So if at any node P, so from a node U, if I can go to multiple nodes V1, V2, V3, can we say dp of V1 is nothing but max of dp of v1, whatever I could get, plus so what is the dp of v1, what is already there, or if I'm coming from, or let's do the other way, both will work. So v1, v2, v3, if these three nodes are coming to node u, then we can write what dp of u is nothing but max of dp of u, or what is the value, what is the total coins at node v1 plus what is the maximum I could get, what is the maximum coin I could get when I reach at v1. I don't know from where I came to v1, but if I know the maximum value I can get till v1, then the maximum value till v1, right, till v1, and yeah, it would be better if I write it like this, plus the value at u, so these two sum or initial value of this. So initially let's initialize everything as 0 or actual number of coins that this node have, because that is the minimum it can get. Okay, now we will have some ordering. So we will have some ordering vector, the topo ordering. We can traverse from that, so that will give me, from here I can go to, from the first node in the node, whatever nodes I can visit, right? If I can visit, let's say v1, v2, v3 from u, I think this would be better. So from this, what is the current value, is nothing but v. So if I go from here to v1, then the v1 will have dp of this plus the number of coins, which is the value of node v1, or dp of u plus value of v2 and dp of u plus value of v3. So maybe some other node also in between is coming to v1, so that will again update. Yeah, so I think we can take max of whatever the value of v1 is initially. It is the shortest path kind of thing, kind of dp. Yeah, so we will apply the dp on this newly created graph, this newly created topological, based on the topological ordering of this graph. I think it's easy. What should we do? First step, let's convert the original graph to the metagraph. Okay, then find the topo sort of metagraph. Okay, then apply dp on the topo sort. Apply dp on the topo sorted graph, topo sort on the topo sorted ordering. I think this should be enough. So how to convert the original graph to the metagraph? I think we would need to find the strongly connected component IDs for every node to which they belong to, and then create the graph, create the new graph. How to find the strongly connected component? I can either use the Tarjans or Kosaraju. I think let's use Tarjan because it is simple. Okay, so first line contain n, m, and then we have the n values k1, k2, Okay. Let's see. M vector. Vector of what is the value of each node? Let's say initially it is 0. We can say go to every node. You can say see the value of I. So in the value of I, the number of coins in every node. Let's say coins. The coins in every room. We get the coins in every room and create the graph. Let's read the as is. The message from x to y, there is a directed as. Would have to maintain the adjacency also. Adjacency of next. Okay. The adjacency of next. Dot in place back. Will there be any place back? Not next, it is x. X to y is an edge. Then we take it as set to remove the parallel edges. Okay. Created the graph. Three times and you can freely choose your starting and ending room. I think that should we run it, or it is obvious. 1 2 2 1 1 3 2 2 4. Okay, so 1 2 belong to one component, then 1 2 3 is an edge and 2 to 4 is an edge. So 1 2 I will choose 5 9. Now either I can go to 3 or I can go to 7. So 9 plus I will go to 7. 9 plus 7 16. Yeah, that is fine. I think, yeah, that's what we need to find. The strongly connected component IDs for every node. Let's write the Tarjans. We can have it in one DFS. On the node U, to write the Tarjan one, you have to find the pre and low linking values. Okay. Pre-order number of each node is -1 and low linking value of each node is 0. Once I come to this node, you can say pre of this is equal to some number counter. Count is equal to 0. We put the count plus plus. Start with 1. Just pass it, or I think it is not required. You can have it defined here only. So count 1 plus, and the low value of this node is nothing but pre value of this node. And go to all the neighbors. Go to all the neighbors of the neighbors of u. Go to all the neighbors of u, and if the value, the pre is not visited, that means pre value is equal to -1. From the DFS on v. So what will happen? So from u, I know everything. Now if I find a forward edge, I think we would need the stack also. Yeah, what is present inside the stack. We need to push this in the stack also. Push this node, right? This is the forward edge case. If it is forward edge, I go and calculate these values for my child, the pre-value, low value, and put the child in the stack. So one node U is put in the stack, V is put in the stack, its child is put in the stack. Now if I from the child, if I come to a backward edge, then what will happen? The low value needs to be updated. Then we can directly write low value of V, not V, low value of U is minimum of low value of U with the low value of V for all the cases. We can write this, and if we find that pre-value of U is equal to low value of U, that means this is the root of that strongly connected component. That means we need to delete everything. No, we need to delete all the nodes till we come to this root node, right? Yeah, because because root is inserted first, root is stacked first, then it's first child, second child. Okay, so true. Let's pop the node. So let's say P, that node is stack.top, stack.pop, pop that node and mark the low value of the pop node as the max value, right? So that this does not and if U is equal to P, if I find that node only, we can break, right? So I think we would need to assign them IDs also. So once I'm popping this node, we can have the SCC to which strongly connected component this node belongs to, SCC ID. Once this is done, SCC ID plus plus, you can have count and SCC ID is equal to 1. Let's try run this code. I think it should work. We'll try it later. Once we have, let's run our DFS. So if the pre-value of node I is equal to -1, we can call DFS on I. Call the DFS on I. It will calculate the strongly connected component pre of U count plus plus. Low of U is pre of U, stack, push inside the stack. Current node, if it is a forward edge, calculate the values for the child. If child comes back to, so from U to V, if I go to a backward edge, back edge or the cross edge, if I go to cross edge, it is already infinite, which is this value. It does not matter then. If it is popped from the stack, then it will have its value as on this value only. Otherwise, if it is a back edge, If it is back edge, then okay, from U I can go to V, and if V can again go somewhere above, then I think, yeah, low we have to take. Yep. And if I find that pre of U is equal to low of U, then while 1 pop from that and stack, pop from the stack, and whatever the node we have got, that is already, like, that means the strongly connected component of that node is already found, right? Low of P is equal to max and SCC of P. If U is equal to P, break and increase the SCC ID. Yeah, I think after this we'll have the SCC ID of every node. So usually it is 0. Now what do we need to do? I think convert the graph to metagraph. We have found the SCC. Let's create this metagraph. Go to all the node, go to all the adjacency node, adjacency of I. So if they belong to different components, SCC of I is not equal to SCC of J, that means from I to J we need to insert an edge. That means metagraph dot pushback meta of, from I we can push the value of J. What is this meta? It should be equal to SCC only, but doesn't matter. It should be SCC of I, right? From SCC of I to SCC of J. From this component to this component there is an edge. Now we need to remove the parallel. We need to remove the parallel edges. So better if we write it as set of this. So parallel edges will be removed. Now I got the metagraph. For this metagraph, I need to find the topological ordering. Okay, so vector of integer ordering. Let's call the DFS1. Let's call the DFS because it will be a DAG, like DFS2 on this metagraph. Okay, DFS2 runs on metagraph by passing the ordering. And which node to start? I think it would be better if we go to all the SCCs. How many nodes are there? SCC ID, is it equal to or less than? I think less than. If it is not visited, what? The I, we can start a DFS 2 from I by passing the ordering. So if it is not visited, because if there is one component only, then SCC will become 2. So I need to just run it one time. And if that node is not visited, bigger node is not visited, we start the DFS at I and ordering. I think one more thing, if there are multiple nodes who belong to same component, we need to sum their values, because and that will be the value of I. So from I to J, that means, can we say that from SCC of I to SCC of J there is a node. So if 1, 5 and 30, these nodes belong to SCC1, then value of 1 should be incremented by the value of, the value of the SCC node 1 should be incremented by the value of 1, number of coins at node 1, number of coins at node 5, and number of coins at node 30. I think we can do that. Let's start a value. It is the pre-low SCC coins. Let's have value also. Everything is 0. What is the value of this SCC? The value of this SCC can store here only. We can run the DFS, not DFS. I think I can write it here only. We can create the graph and then the value at SCC of I, so that should be incremented by the coins at node I, right? So if I belongs to SCC of I, so all those nodes who belong to SCC of I, so they all should contribute to that bigger node. I need to find the ordering of this bigger node. So I and DFS2, I and ordering, pass the I and ordering. Let's write the DFS2 which finds the ordering. DFS2, what is the node? Vector of integer, ordering. I think, yeah, so let's visit this node. I have visited. I would need to have a vector of boolean visited. Everything is false. Okay, if it is not visited, then in the DFS, then visited of u becomes true. Now get visited and go to all the neighbors. It is not the adjacency, it will be the meta of u. Go to all the neighbors of u and go to all the neighbors of u and what? And if this is not visited, call the DFS2 on v with the ordering, and once I'm done with this, then ordering dot pushback and place back what? U. So after this we have the topological ordering. I think we need to reverse it. Okay, now we can do the DP thing. Into DP, how many SCC ID? Every node has 0. We can traverse over the I over the ordering. From I, which nodes I can go? So they are nothing but J over the adjacency, not adjacency. It will be the meta of I. From I can go to this node, J node. So I can write the dp of J is nothing but max of dp of J, the current value, or from which node I am coming to. From which node I am coming? I'm coming from node I, right? And the value of J, yeah. What will be the answer? Answer will be the node which has the maximum value. CCID I++. Answer is maximum of let's run dp of I. It is not required. Okay. I'm not sure will it work or not, but let's see. Of course there will be bug. Too few arguments in DFS 26.7. B and the stack st also. I'm calling the DFS. I need the stack also. Yeah. Need the stack also. Class set has no member pushback. 8221. Line number 82. Meta.insert. Okay, now errors are gone, but let's dry run this before submitting. Change this. Do so first let's read nm. Okay, go to every node, read the number of coins in that node. Okay, and then read the edges x to y, insert an edge. After that we need to find the SCC ID of every node. So go to every node. If the pre value is -1, start a DFS from I and pass the set. Okay, so DFS 1, how it is working. So I'm at node U. How it should look like. So if I'm at node U, as long as I'm getting the forward edges, I will keep on inserting them in the set, right? So it is inserted in the set, it is in the set. Now if I get a back edge from this node, let's say it is a back edge from here, so pre-values will be updated also. Let's say pre-value is 1, 2, 3, 4. Now the DFS will keep on going. Right. So DFS will keep on going until as long as I am getting the forward edge. Now in the case when I am at the leaf node, at this node, I get a back edge, and I'm saying low of U, whatever is the low of V. So at that time U will be this one. So for this node there is no forward edge, it is going to a backward edge. So for that node it will come and calculate the pre as 4, low as 4, push it in the stack, push it inside the stack. I think this is also push in the stack, push it inside the stack, and at this point it will not have this thing. It will have low of that node is equal to low of this node plus and low of this node. So that means what will be the low value of this node? It will be, so initially I have marked low value is equal to pre-order number, so it will have low value as 3. Now for this node, now DFS will return back to this, not 3, it will be 2, right? Yeah, it will be 2. Better if I write it here, 4, 2. Now DFS, it will, what will happen? it will be done for the parent, and it will also calculate its low value, which is nothing but the parent's value. So it will also become 2. It will also become 2, which is already 2. So once the call is getting over, so at this node, I think this will be hit for only this node. Yeah, so I think this node, the pre-value and low values are equal. Pre-values and low values are equal. That means whatever is in the stack, keep on deleting. So which nodes will be deleted? So this node is deleted, this node is deleted, this node is deleted. Yeah, so keep on deleting, keep on popping from the stack, and mark the low values as infinite and assign them as the CC value of 1. Right, once I pop the parent node, yeah, this red node, that means I need to break. So what I can say, this, by this tree, this thing belongs to one component, yeah, one strongly connected component, and for this one HCC will be 2, which will be popped from the stack later. I think if it is parent node, so it will again be popped. Do I need to handle it here? I don't think so, because if suppose it is a straight line, what will happen? A straight line, so I call DFS from here, it will push in the stack this one, push in the stack this one, push in the stack this one. Now it doesn't have any low value, so it will be popped from the stack. Yeah, then it come here, it will again be popped from the stack, because low and pre are equal. It will be popped from the stack, it will be popped from the stack. So there will be 4 strongly connected component. This node, this node, this node, this node, all of them are different. I think this will work. This will work for the strongly connected component IDs. After this we have got, we initialized pre as -1, low, and SCC. Okay, then what I am doing, I go and create the metagraph for I equal to 1 to n j if they belong to different components. That means there is an edge from I to j, and there can be parallel edges also. That means meta should have the set. Does it have set? Yes, it has set. Inside the set of I to j, insert this edge only one time, and I was belonging to all the nodes which are belonging to strongly connected component 1. So this meta node will have this value. Yeah, initially it should have 0. Val is 0. Yep, I think, yeah, val is 0. After this we have the value. Now I need to find the topological sort of this metagraph. How to find that? Go to all the nodes which will be max SCCID, and if it is not visited, then apply the DFS, call DFS on that node. Okay, DFS2, what it is doing, mark it visited, go to any unvisited child, unvisited neighbor, and do the DFS on V with the ordering, and once it is done, in place back U and reverse the ordering, we get the topological sort of this metagraph. Now I need to find what is the maximum coin I can collect, right? So I think every node, yeah, this is tricky. So let's say I have the metagraph like this. What will happen? So in the topological sort, so first it will be visited, then this will be visited. So we can visit anything from here, here, and here. Okay, so it will it will apply this one. So what it will say, whatever the value is it has currently, that means dp of everything should be equal to the value of each node initially. Yeah, so once I come from here to here, then dp of this is what? dp of this, well, this node plus whatever the value I am getting here, so that will be my new value. And what is the dp of this value? Yeah, it should be initialized with the value, initial value, not 0. I think this is wrong. We can go to each node CCID. I think it's better write it here. You can say dp of I is nothing but the val of I, right? Because value is already calculated for every component. We find the dp of I initialized with the current value. Okay, then reverse it and then apply the dp. Okay, so from I go to j in the order, in this topological order, meta of I. From I go to j, that means j value should be the value at j plus what was the value at I. Yep, then I can have the answer equal to 0 and go to each node, go to every SEC and maximize that answer, and that will be the answer. Yeah, I think this will work. Is there any possibility to have long? Yes, 10 raised to 9. I think dp should be long. dp should be long, value should be long. Okay. Value is long. Then we are calculating this value of each node plus equal to, then dp should also be long. Yeah, where is the dp vector? What is the error now? To call the max, it cannot call max on int and long int. Okay. Let's see if it works. Wow, it worked. Great. First go only. Yeah. It was a good question, huh? I had to do a lot of things. First I created the graph, the metagraph. For metagraph we have to implement the Tarjan's algorithm. Yeah, Tarjan's algorithm implemented, then got the metagraph. We created the metagraph, which is this one, and then for this graph, for this second graph, I have to actually calculate the graph and assign the values also, which is the combination of this, and I have to find the topological sorting of that graph and then do the DP on that. ठीक है. Okay.